In this video, we're going to look at determining congruence in plane space. So remember our key ideas here that two figures are congruent if and only if one can be mapped onto the other using one or more rigid motions. Rigid motions are preserving our angle measures and side lengths. And then our second key idea is that translations, reflections, and rotations are the rigid motions. And any combination of those will map one figure onto another will justify that those figures are congruent. So if we look at this first example, notice we're not on a grid anymore or on a graph, but we're going to still kind of use the same idea. So we're trying to figure out how can I get from one figure to the other using one or more rigid motions. So in this example, we want to use transformation or sequence of transformations to explain when a transversal crosses parallel lines. So we're going to assume that these are parallel. We want to show that alternate exterior angles are always congruent. So we're just kind of looking for how could we show this? How could we map one angle onto the other? So keeping in mind here, let's identify a pair of exterior alternate exterior angles. So 2 and 7 are alternate exterior angles. So what I want to do is I want to pick one or more rigid motions that'll take 2 and map it onto 7. So the same thing can happen from 2 to 7, and then we could do the same exact reasoning for 1 and 8, and I'll make a note of that later on. But for right now, we look at angle 2. If I were to take angle 2 and rotate it 180 degrees around this point, which I'm going to call point A, so if I rotate angle 2 180 degrees, this ray right here is going to move 180 degrees and end up down here. And this ray right here, if I rotate 180 degrees, would end up over here, making angle 2 congruent to angle 3, since a rotation of 180 degrees would map one onto the other. So that's the first thing I'm going to mention, is that a rotation of 180 degrees, and for rotating 180, you don't have to specify direction because either way it's going to end up in the same spot. So rotation of 180 degrees around point A, and you could put any point you want there, will map angle 2 onto angle 3. So there's the first part. But remember, I'm trying to get down to angle 7. So the next thing I could do is if I take angle 3, so imagine this section right here, and if I translate that down along this vector, so from A to, let's say, point B, if I take this vertex and I translate it down, it's going to end up here. If I take this section right here and I translate it down, it's going to end up right here. And since these lines are parallel, whenever we translate, it's going to create parallel segments. So this piece will translate right down onto here. And then the bottom part of the angle is really just sliding along that same line. So what that's going to do is it's going to map angle 3 onto angle 7 using the translation, making them congruent to each other. So now I'm going to mention that. So then I'm going to say then angle 3 maps onto angle 7 using a translation. And remember, when we talk about translation, we have to state the vector, so the direction and the distance. So in this case, I don't have any numbers to work with, so I'm just going to say along this vector AB that I've sketched in there. So angle 3 maps onto angle 7 using a translation along vector AB. And then since that basically takes angle 2, maps onto angle 3, and then angle 3 becomes angle 7, that's showing that angle 2 is really mapping on to angle 7. So thus, or therefore, I could say angle 2 maps onto angle 7 using a sequence of rigid motions, meaning a rotation, then a translation, which keep angle measures and side lengths, but I don't really need to mention side lengths here because I'm talking about angles. So I'm just going to say using a sequence of rigid motions, which I forgot the word keeps, which keeps, so let's add that in there, that's important, keeps angle measures, making those angles congruent. So making angle 2 congruent to angle 7. So then similarly, I could show that angle 1 and angle 8 are congruent using the exact same approach. I could rotate angle 1 180 degrees onto angle 4, then I could slide angle 4 down onto angle 8 using that same vector. I'm not going to write it all up again, but I'm just going to make a note here that we could use the same approach. So I'm just going to say note, angle 1 is congruent to angle 8 using the same approach. So therefore, if the lines are parallel, those translations are where the parallel comes into play. It's making those angles map onto each other, making those alternate exterior angles congruent. So that's the idea. It's not an official proof. It's just basically thinking about how could you take one angle and map it onto its corresponding alternate exterior angle to show that those angles are congruent using a sequence of rigid motions. So let's do the same process, but let's look at a couple of triangles instead. So notice again, there's no grid. They give us some information that we can use. We can mark the diagram. But again, we're going to kind of do this informally where we're really just looking at how can I map one onto the other. So it tells me perpendicular, so I mark that as right angles. So we want to figure out some rigid motion, so a rigid motion or a sequence of rigid motions that will map one triangle onto the other to show that they are congruent. So a couple ways you can do this. Again, you can check that orientation. So look at the order of the letters. I can say B, A, C, and then if I go in the same order here, so X, Y, C, and you can see that all my arrows are going in the same direction. So that means it's the same orientation, which is telling me that it's got to be a rotation or translation. And in this case, I'm seeing a clear turn. So that tells me it's a rotation. So I have to figure out, well, how many degrees? The fact that I have a right angle here tells me that if I take and I rotate this triangle 90 degrees, this right angle is going to map onto this right angle right here. So basically, I just need to turn it 90 degrees. So let's say I'm starting with triangle 1. I'm going to map it onto triangle 2. I could do a rotation of 90 degrees clockwise. So a clockwise rotation. And notice point C stays in place, so that tells me that that's the angle of rotation. Since they tell us we have some congruent pieces here, I know for sure that AC is going to map onto YC if you do a 90-degree rotation because they're congruent. And then also we could say that these other pieces are going to map onto each other. But really, we're just looking to identify what happens, what rigid motion happens. So to write this up, it's going to be very similar to what we saw in the coordinate plane. So I'm just going to start by saying these triangles are congruent because rotation, and we need to make sure we state all three things. So rotation of 90 degrees clockwise, so my angle, my degree, and then the point. So because of rotation of 90 degrees clockwise around point C will map triangle BAC onto triangle XYZ. Make sure you're paying attention to the order here, because if I switch this and said XYZ gets mapped onto BAC, well, now it's not a clockwise rotation, it'd be a counterclockwise rotation. So make sure you're careful. Because a rotation of 90 degrees would map the triangles onto each other. And then I can just simply add in, so I stated the specific rigid motion, and now I can just say rotations are rigid motions which preserve angle measures, and side lengths, which is what will keep the same shape and the same size, making those figures congruent. So that's not an official proof. Transformational proofs are much more complicated than just that. But this just kind of gives you an idea of how you could get one figure onto the other and why they would be congruent. So go ahead and do the check your understanding page and just make sure you're including the same kind of write-up. So you're talking about stating the transformation or the rigid motion that occurred, and then just that justification, that those rigid transformations preserving angle measures and side lengths.